Okay, this lecture series, we're going to talk a bit about genetic screening as it relates, of course, to humans. And I'm not going to get into every genetic screen or genetic test. I mean, we could do that, but there are hundreds of them. There's more every week. For the most part, they involve either sequencing or very often just PCR. So most of us know, I mean, we know now what that is, and certainly, so the methods are not that critical to know more about. And you could do a web search for any genetic test you want to look for and see how they work, what they detect, what mutations. So I didn't think spending a huge amount of time walking through a large number of those was really very beneficial. We'll talk about a couple, but in general. But what I thought was more important was maybe to talk a broader picture about genetic testing. So what I want to do in this first lecture part is to talk about genetic screening and genetic testing and how those two terms, how they're used, okay, and what they mean, and some of the subtleties of these, because they're kind of important if you're looking at the outcome of a test and trying to understand either personally or professionally, trying to tell somebody what this really means. So I thought I'd talk about that. Then we'll talk about genetic testing and some types, just go through some examples of how we might do those and some of the issues that may come up. And then finally, we'll end up talking about some legal and ethical issues. And we've already covered some of that. We'll just expand on a few additional things. So at least for this one, let me start out with genetic screening and testing and sort of look at those. So what is genetic screening? Well, genetic screening, laser pointer here. Genetic screening is applied at a population level. That's what screening means, okay? It's a group sort of thing. And it's been done forever. We've used it to look at things like estimate the frequency of alleles, frequency of mutations, frequency of diseases. We want to know in a population of X, what level do we have? And we apply it to animals and plants. And of course, this course we're talking about humans. So we want to know in a certain population, what's the frequency of the A allele, of the ABO blood group, right? That's a genetic test. Very, kind of primitive in the way we used to do it, but it was a test. What's the frequency of the B allele? What's the frequency, of whatever, or AB genotypes, and of course disease as well. Now, we use this to identify things like subpopulations with a higher frequency, particularly when we're talking about disease or mutations. Examples of that would be Tay-Sachs. It's found among individuals who are historically of Hasidic Jewish populations, certain regions of the world. Sickle cell anemia, sickle cell trait, was prevalent in areas of high malaria content. So in areas of Eastern Africa, Southern Africa and Central Africa and Equatorial Africa region, but particularly in the eastern side of that, we see a much higher propensity of that particular mutation in those subpopulations and individuals who originated there. So it's interesting for that. We want to identify carrier frequencies, because remember, a lot of genetic diseases, particularly before we could truly test at the genetics level, but when we were looking at trying to relate it back from the phenotype, they were very often recessive, right? And so we have a dominant would be the non-affected or the normal part, and then you would have individuals that would have the disease, and very often they were recessives. Phenotypically. And so what we were interested in and what genetic counselors were interested in is figuring out with the carriers, right? Who's got it? Who's the heads? And so you're not, so you had to estimate that, and we'll talk about it in the population genetics part when we get to that, how you actually estimate it. But you can estimate the number of carriers from a screening. Once you know how many people actually have it, you can estimate how many people are carriers, and so it's very important data for use in that sort of thing. And then, of course, you can still use it to identify individuals who may or may not carry the trait themselves. Okay, as part of this carrier frequency, pinpointing with if you can identify, okay, you're from a subpopulation from somewhere in Utah, and or you're from wherever, Mali or somewhere, and this frequency of this allele is high there. The carrier frequency is this. We can use it. All right, now when you do genetic screening and develop genetic screens, genetic tests, and you're screening for it, you end up with some very interesting issues and terms. And so there are a couple of ideas here. You think about it, this blue part over here are individuals who are affected with little red dots indicate those individuals who actually have the disease, okay? Or a trait. It doesn't be a disease, a mutation, you could be after, whatever you're trying to work. All right, when you develop a genetic test to screen these individuals, those genetic tests have several terms related to them that are very important, okay? One of those terms is the sensitivity, and the other is the specificity, okay? And those are two terms that are really important, and we're going to talk about how they're calculated and stuff in just a minute. But here's our example, okay? We've got a group, this blue group are individuals who are affected, okay? We go and develop some genetic test, okay? And we were able to identify true positives, that's the little people with the red dots, about 80% of the time, okay, 0.8, okay? We get some false negatives, okay? There are some people that have it, but you obviously back here couldn't detect it, so they would be false negatives of around 20%, okay? If we take that and we look at the unaffected population, and that's usually how you test these things, right? You do these randomized tests, and you set up a group that's unaffected, a group that's affected, and you go in and you test both sides, and you try to merge those to see how good your test is going to be, right? Well, if the unaffected group, we get true negatives around 60%. We get a bunch of false positives around 40%, which is not unusual. We're just doing it out of 100 here to make the math easy. You can take those numbers and put them together, and you can estimate the sensitivity and the specificity. And again, I'll show you in a moment how the actual numbers there, but you take the true positives and the false positives and you put them together and you do a little bit of trivial math. Okay, now those are two very important values, right? They are critical to our understanding of things. So let's just take a look. So this is an example where we've got a test and we're going to play with it, which we've got the sensitivities around 80% and the specificities around 60%, okay? We'd like it to be 100% both ways, right? We'd like to be 100% of it would have sensitivity, okay? And we'd like the 100% specificity, okay? That's what you'd like, but no test has that, okay? And in fact, there's a trade-off between the two. So what are they? Let's just do the definitions first, and then we'll talk a little bit about what they are and how to calculate them. So this idea of sensitivity. Sensitivity is among the people with a specific condition, okay, so people that are positive, the proportion that will give a positive test, okay? So you can actually detect, so I've got the mutation and you can detect me, that's the sensitivity, okay? Specificity is among people who do not have the condition, the proportion that will give a negative test. So I don't have it and I want to make sure I know I don't have it, okay? That's the specificity problem. Okay. All right. Those are interrelated, obviously, and generally, if you have high sensitivity, you may not be very specific, and sometimes very specific, you may not have high sensitivity. Okay. So those are interplays, and things. Give you a real world example. Let me see if I can do that. Okay. Here's a way off the subject. It's not a genetics test. Okay. But almost all of us have been through TSA now, right? I'm sure everybody has. In TSA, you go through, the objective in TSA is to have high sensitivity. They want to have nearly 100% sensitivity, okay? In other words, if there's something going through there that's not supposed to be going through there, they want to be able to detect it, okay? They have terrible specificity, okay? They, if you think about it, and if you've ever been through, I know even though I'm a trusted traveler and all the little paperwork, fingerprinting and things that they do so you can travel and not have to go through the regular lines, I still go through the other lines. I've been pulled out a number of times, okay, because I have lots of cords and cables and I take my drone with me and my fishing rods and all sorts of stuff. And so I get pulled out all the time. Why? Because this thing's sensitive to there's something in there, okay? But it's not specific. It's not saying, okay, it's a dangerous item or it's not a dangerous item. It says, whoop, comes up red. So those are the two differences, and that's the way the tests work, right? We have high sensitivity, don't necessarily have high specificity. Okay, just working it. Now, all these fall under what are known as clinical validity. Okay, we're going to talk about clinical validity, and then we'll talk a little bit about clinical utility. But when you start developing tests, genetics tests, or well, any test, but genetics tests in particular, you try to balance these two ideas or these two concepts. One is the validity, clinical validity. Is it actually working? Okay. And one of the real problems you see is that there's all this stuff thrown out in the literature, or the news, I'll say, about whether say, oh, a test is 99% positive, 99% successful. And that's certainly been going on recently, with the tests and things, viral tests and things. We got this test is going to work and blah, blah, blah. And those are, and it affects things like the stock market, right? Where this company will announce that they've got a new test and the sensitivity of it is, 90% or something. And people just go, oh, okay, it's great. Because you want it to be 90% or so. But reality is it doesn't have much specificity, okay, or something. It does one thing okay, but it doesn't do the other thing okay. So what you really should look like, and in particularly what clinicians look like and people that do research working with genetic tests, is they look at these other values called the positive predicted value and the negative predicted value. And it turns out those, even though these can be quite high, these might actually be fairly low. And so what are they? Well, positive predictive value is among the people that test positive, okay? Those are the people who actually do have the condition. All right, that sounds a little strange, but it means I got a positive test and I actually have it, okay? And that's really important because it's you want your test to have a lot of accuracy to it and not be scaring people to death. You're testing for a cancer mutation and half the people that test positive actually don't have it. Well, that's not so good, right? You're going to scare half the people that for no real reason. The negative predictive value is just the converse of that. It's among people with a negative test, the proportion that do not have it, okay? That also you want to be high, okay? You don't want to mess up and miss people, right? So a negative predictive value. So when you really look at tests, if you're ever out there trying to figure out whether this test is worth it or not, which is not clinical validity, it's clinical utility. Okay, that's a different term, a different idea. But part of trying to figure that out, whether it's useful or not, is to figuring out whether these values and what they are. So how are they calculated? Well, trivial little math and something you don't need to memorize or anything, but specificity is the number of true negatives divided by the number of true negatives plus the number of false positive. I said, let me go back for a second. I said, we're going to use some values from over here, the true negatives, the true positives, and we're going to mix them together, right? And that's really all we're doing here, okay? Sensitivity, okay, so that's specificity. That's trying to remember specificity is about, can I get it correct about a number that don't actually have it? Sensitivity is, okay, I want to be sensitive, so I want a number of true positives divided by the true positives plus the false negatives, okay? Remember, because that's one where, things. That's the airport example. We get a lot of false, get a lot of these. Yeah, there's some true stuff. They get people loading guns and all kinds of weird stuff in their luggage, hand luggage, thinking they go through. We also get a lot of other things. All right, what are the predictive values? These are the ones you're interested in. Number of true positives divided by the number of true positives plus the number of false positives, okay? True positives plus the number of false positives gives you my predicted value. In a positive way, negative is just a reverse. True negatives divided by the number of false negatives plus the number of true negatives. Okay, very simple math. So why am I calculating this? Well, because it's important to understand when you're doing these screenings what kind of accuracy and quality you're getting out of your data. So let's take this one. Let's go back to our genetics test. we've decided that the specificity of this is about 60%. The sensitivity is about 80%. Sounds pretty good, right? I mean, that's a pretty good test, I would think. We'd like to be up around 90, but you know, this is a test, a genetics test. We're doing okay with it. So people are throwing out all these numbers, right? They're sitting there going, "Wow, you know, I got this new genetics test, and it's detecting an 80% accuracy. 80%. Well, that's not accuracy, okay? That's the sensitivity of the test. All right, so let's divide that into what we have. So let's take a population of 100. And let's say that in reality, there's 5 individuals in there that have whatever you're testing for, you're screening for. Okay, so the prevalence is you know, 0.05, 5%. Okay, this genetics test, we're asking, can we find these people? Okay, can we find them, and how well do we do? Well, if you take these levels and you do a positive test, okay, you ask who's positive. Because you're at 0.8, you're going to miss some 20%. Okay, so 20% of 5 is 4. Okay, so true positives, you're going to be able to detect 4 of these guys. You don't know which 4, but you can get 4 of them. Okay, your sensitivity is not very good, right? You're going to get a lot of false positives. So you're going to get about 40% are going to be false positives. So you multiply 1 minus 0.6, right? 40%. Times 95, that's the remainder of the individuals here that don't really have it. And you get about 38 individuals that are going to give false positives, okay? So you're going to get this pile of individuals. Yeah, you're going to detect, you know, some of them, but you're not going to get everybody, okay? All right, so we've got 4 people tested that have it, okay? We missed one completely, all right? That's the one that's going to end up over here. And so what's our positive predictive value? Is about 0.095. So the test, people would be counting that the test is good at 80%, you know, the accuracy. Really, it's not very good. The positive predictive value of this test is pretty crummy. Why? Because you're getting so many of these individuals that are showing up positive when they're false positives. Okay, so you know, and just moving these a little bit can really help that. Okay, we'll see that in a moment. Right. Well, that's one of the big things here. Okay. Yeah. Okay. Let's say it's a really, really dangerous disease or a really, really dangerous problem. And I don't mind telling a bunch of people that they have it when they don't, because we'll go through a secondary screen or something. Okay. That's okay. All right. Maybe it's cheap or something. Okay. It's simple. But if it's not, I mean, it's a lot of people out here that you have that you've come up with as a problem, including some individuals that should fit over here. So you've got a real problem in the sense that it may ethics, all sorts of other things. You may have told people things that that they have certain things that they don't, and it goes back to some of those questions about the when first tests that were out for sickle cell carriers, sickle cell trait. And that affected people's lives for years when they were given a simple little test back in the late 60s about sickle cell trait, right? And if you tested positive, well, it had a lot of false positives to it. And if it did, I mean, it was a bad test anyway, because the data was used in a completely bad way. But then you also had a long-term effect on people's lives by telling them that they were a carrier for sickle cell and when they weren't. Okay. Now, what about the other side of it, the negatives over here? All right, that's the negative predictive value. Okay. Well, in that case, we've got the true negatives are about 95 times 0.6. So even though that specificity is not great, you're still pretty good at picking that out. Okay. False negatives, you don't get a lot of false negatives. Okay. You did miss one person here out of the 5. Okay, but that's not so bad. So the negative predictive value is pretty good. Okay, it's about 98%. So it's doing quite well, right? So remember, again, this is that calculation that we just did off the last slide, where we take the number of true negatives plus the number of false negatives and use them to calculate it. So really, it's got that side's good. This side is pretty bad. Okay, so how might we fix that? Well, we might make a better test. We might somehow take this out, the values of sensitivity and come back and say, no, we've done more testing and all that sort of thing. Okay. And how do you get into situations like this? Well, one of the ways you get into situations like this is that a lot of a lot of tests, once you go out and you grab a population to test them with, are people who have the disease, large potentially have disease or do have the disease. You test, you're developing a test for prostate cancer, you got a new screen for it. Who do you go screen? Well, you tend to over screen people who have prostate cancer, right? Because you want to know if it works, right? You want to know that it could detect them. So we did a lot on the positive side. There's usually not as much on the negative side because it's expense and they don't have it anyway. Now in modern times and since statisticians have gotten a hold of this, and so randomization tests are done to really bring in that and make a strong paper and make a strong study. All right, well, how else would you fix it? Can you think of a way that there's something that might help here? Okay. Well, there's lots of things, but one of the common things that's done is, why am I sampling all these people down here that I'm pretty sure don't have it? Okay. Maybe there's a way to cull out some of these. And this is some of the things that genetic engineering does. Okay. Is that it sort of, genetic counseling does, is that, it gets rid of these people. And what's that? Well, that's called pre-screening. So we look at family history. You're interested in something like heart disease, or you're interested in high blood pressure or diabetes or whatever. Well, if there's no history of it, maybe you don't need to test those people. Okay. So if you can just simply get the numbers down, then you're doing well. Because think about it, we've got 5 people over here out of 100 that we're testing. Okay. Prevalence is low. Here we've got high prevalence and et cetera, because we've got 5 out of, say, 25. Okay, I made it math, make it easy. Okay, well, look what happens there. We take the same test. Okay, we go on the negative side. We're still going to get up around more than 90% success in the negative part of it, right? Okay. And we're going to increase our positive predictive value to about 0.33. Now, that's still not great, okay, but we're doing a lot better, okay? Why? Because we've got all these individuals that, we're able to pick them out. So even if we detect basically the same exact number of individuals, we don't have as much of a chance of having so many false positives. So this is what some genetic counseling and other things do, right, and in studies. So this is one way to do it. Okay, it's sort of just making your population that you're screening more precise, and you do it so it's a pre-screen sort of idea, right? And so it sort of helps. That's one of the things that they do, and they actually do that in the TSA. If you think about it, because you got some people that you go through and they mark your little thing, and you're going to get screened no matter what, and they think you need to be screened. Okay, and so they will screen it. All right, that's screening. That's some of the ideas and some of the things to be careful about. Again, this would be 80%. They'd be all over the papers and all over the websites about how great this test is. And it's not so great for some things, so you have to really think about that. Okay, so what about genetic testing? Well, in genetics, usually the word testing is usually, and again, it's kind of like the word allele and stuff. It pops and had different meanings in different places. But generally, when we're talking about here, we're talking about it at the individual level. Okay, we test at the individual level. And what are we trying to test for? We're trying to identify individuals who have or could carry a trait. Okay, so individuals, that's the big word here. Okay, individuals. And we can do it to identify individuals who are at risk of having a child or something. And that's really often where it comes in. We test to say, yeah, the 2 of you are pretty sure both of you are carriers, and your percentage is going to be, 1 out of 4, or whatever their tests are going to be. And, we test to identify those who have a genetic sensitivity. So what are the things like disease? Okay, you can test for people who have a propensity that they may have breast cancer, they may be exposed to things, black lung disease or whatever, may have a propensity for that. Certain types of drugs. And that's becoming more and more important because we're doing designer testing now, because there are more and more pharmaceuticals will be aimed at a specific type of part of the disease or specific mutation. You may have 10 mutations or 20 mutations from different genes or something that all relate into this one disease. But if you can, specifically go after this one, you say this person only has these 2 mutations, not these 4. Maybe there's a different drug that'll work to help that individual out. So there's, designer drugs, designer testing, and things like environmental agents, individuals that are susceptible to, like I said, black lung or to asbestos exposure or to environmental exposure. So it can be useful for sort of that. Okay. It works well. And a little chart over here, showing you genetics tests can pinpoint genetic diseases and predict how severe your disease might be, because different mutations have different ones, best medicine, risk factors, and all sorts of things. Okay. All right. So where do we see this? All right. Well, genetic testing done all over the place, more and more and more of it. Medicare, one of the things, will even pay for some genetic pre-screens. There's a growing list of how many of those are. I think cancer, they only screen for colorectal cancer or something. They'll pay for that. But there's that. And you can see this is back in, almost 10 years ago. And you see that there were thousands of tests, but just by Medicare. I'm not including the other insurance companies or other testing that was going on. So you see, here's Maine with not very many people in it. It did 35,000 genetic tests in that one state. Okay. Here in Alabama, back then we had about 18,000. There were a few more. Mississippi, Louisiana had a stronger. Florida had even more. They were paid, again, out of Medicare. That doesn't mean this is the total number of genetic tests. There were many, many more genetic tests. And these can be done for all sorts of reasons, right? Forms. But I just wanted to show you that there are a lot of genetics tests being done, a lot of them out in this country and throughout the world. Okay. All right. So that is the end of genetic screening, genetic testing. The next lecture, we'll talk about just an overview of types, including carriers and pre-symptomatic and others.